Now continuing on, we will talk about some of the simulations and predictions of the IPCC Summary for Policymakers report. Many different computer simulations or models have been written to simulate the atmosphere. For example, some of these models you're very familiar with because they're used to predict weather or the day-to-day weather that we see on TV. So we depend on weather models when we're trying to figure out what we want to wear to go out to see friends, or if we're going to work in the morning. Is it going to rain? Is it going to be cold or warm? And we depend on these weather reports to figure out how to go about our daily activities. Climate models have many of the same features programmed into them as weather models, so they include many of the same variables like cloud cover and humidity, and the temperature leading up to it, and solar radiation, a lot of the same things. But climate models are over a larger geographic and a longer time scale. So what do climate models include? They also include variations in incoming solar radiation, volcanic activity, and clouds. So volcanic ash and clouds both can block and reflect incoming solar radiation, so they're actually very important for climate models. These climate models also include changes in land use, because land use in turn changes how much solar radiation is absorbed by the land surface versus reflected. So an icy surface is going to reflect most of that solar radiation back out away from Earth, whereas a dark soil surface will absorb much of that solar heat energy. These models also include natural and human aerosols, plane contrails, and greenhouse gas emissions. So note that some aerosol emissions will lead to cooling because they can reflect solar radiation, or they can seed clouds that will reflect solar radiation. So we have three charts on this slide. The chart on the left is just saying this is the overall observed warming that we've seen, and it's adding up all of the different contributions in these climate computer models to show that we've seen a 1 degree temperature increase on the Celsius scale, and it's as a result of all these different factors that are included in those climate models. The chart in the middle shows overarching categories, which are further subdivided on the chart that's on the right. So the chart in the middle and the chart on the right have the same categories, it's just they're further subdivided out into smaller categories in the chart on the right. Red bars are showing factors that increase global temperatures, and blue bars are showing factors that cause decrease in global temperatures. And so you can see things like aerosols can cause a decrease in temperature, but greenhouse gas emissions, carbon dioxide, methane, nitrous oxide, these are all causing an increase. These are all red bars. And so overall, the red bars are winning on this group of factors on this graph. And that means that greenhouse gas emissions are the main driver that is causing our global climate to warm over time. So in the last slide, I mentioned that many different computer simulations or models have been written to predict climate change. These models are calibrated or programmed using climate data from the past, so data that we've collected in the past. And for that reason, all of the models fit very closely to the line of historical data that was used to program them. So in the top chart here, we see historical global warming shown in the gray area and this black line. And you can see that the climate models were programmed with this data, so there's no difference between the observed and the climate model data. It's all the same because they were used. The actual data was used to program the models. So these are it's all together here. But beginning in 2020, from here on out, we have to use these models to predict what's going to happen. We don't have data because it hasn't happened yet. And so that's what these lines and shaded areas are showing on the graph on the right side of this graph. So we're seeing 5 different climate models, and each one is showing a different level of warming and a different level of uncertainty, which is represented by the width of that band. So the main difference between these different models are the amounts of CO2 emissions that are going into the atmosphere. And rather, these models are assuming how much CO2 is going to go into the atmosphere. So some of these models are very optimistic, and they're assuming that humanity, that we're going to get our act together, we're going to decrease emissions, and other models are less optimistic, and some of them, like 3-7.0 and 5-8.5, these both assume that we will continue to increase emissions as we have been doing even in the last year, and that these emissions will double by the year 2050 in the case of 5-8.5, or the emissions will double by the year 2100 in the case of 3-7.0. And this will result in a net temperature increase of between 1.5 and 3 degrees Celsius. The model 2-4.5 is kind of a moderate model, so it assumes up to about 2.5 degrees and down as low as 1.5 degrees Celsius increase change. And then the optimistic models, 1-1.9 and 1-2.6, both of these assume that we will be carbon neutral by the year 2050, and that we may even start to have negative emissions as we plant trees and other mitigation steps that will absorb some of the greenhouse gases from the atmosphere. And so these more optimistic models predict a temperature increase in the future of only 1 to 2 degrees Celsius. And that's, of course, because there is still carbon in the atmosphere, and we will still have carbon in the atmosphere in the future. So even if we stopped emitting carbon today, we would still see an increase in temperature because of the carbon that's already in the atmosphere. And then in these models, because of the carbon that will still be emitted until the year 2050. So again, these models really differ mainly in their assumptions about the amount of greenhouse gases that will be emitted in the future. So on the top left part of the slide in the graph, you can see the very optimistic blue models assume that we will continue to emit some gases, so the little bars for CO2 are small, relatively small. So we will continue to emit some gases until we taper off by 2050. Furthermore, they assume that CO2 levels will begin to decline in the atmosphere after 2050. And so on the graph down below that shows the predicted global surface temperature change, we see that the temperature increases until 2050, and then these blue models predict it will very gradually start to decline shortly after that. The less optimistic models, shown in red, you can see that they're predicting these large bars on the chart of CO2 emissions. So they're predicting a lot of CO2 is going to be emitted in the future. And as a result, you can see that the temperature increase on Earth's surface is predicted to be much higher in that scenario. And so in scenario 5-8.5, we expect up to a 5 degrees Celsius temperature increase by the year 2100 if we continue to emit and increase our greenhouse gas emissions. Of course, as the climate warms, we don't expect to see that everywhere is going to increase at the same rate. Some areas will see more heating and some areas will see less heating. So those previous graphs were looking at global averages. So when you start looking at impacts on people in different regions, one thing we look at is how these models predict extreme heat events will occur in the future. So for an extreme heat event that used to occur only once every 10 years, we are currently experiencing these events 2.8 times as often. And if the climate warms by 4 degrees Celsius, we will experience these events 9.4 times as frequently. So instead of once every 10 years, we'll experience these 9.4 times every 10 years. So basically once a year. Furthermore, we will see an increase in super extreme heating events. So heating events that maybe only used to happen once every 50 years will happen about 39 times over 50 years. So 39 times as likely if we see a 4 degrees Celsius temperature increase in the next 50 years, 50 to 100 years. These global maps show how the average global temperature change will translate to different regions on the globe. So as you can see, some regions, such as the polar regions, these are very dark red compared to the rest of the globe, and they will see much larger increases in average temperature than areas over the ocean, for example, in the tropics. So certain areas on the globe will definitely be impacted to a greater extent than other regions on the globe. Already, we're seeing increased flooding and increased drought in many regions across the world as a result of climate change. This table shows how much more likely these flood and drought events are under different warming scenarios. So this helps policymakers to decide how much warming can we really afford to experience and what would be the cost or the likely outcome of this event. So on a global scale, we may wonder, where do we expect to see more droughts or more floods? The maps on the bottom, in the box on the bottom, are brown in areas that will receive less precipitation as global atmospheric temperatures increase. So these include parts of the Caribbean, Central and South America, Southern Africa, Middle East, and parts of Australia. On the top box with 3 global maps, we are seeing how soil moisture will be affected by increasing global average temperatures. And you can see that many regions across the globe, which are also shown in brown, will see a decrease in soil moisture as temperatures increase and sometimes as precipitation decreases. So we said even if precipitation does not decrease very much, an increase in temperature will still lead to more evaporation from plant and soil surfaces, which leads to a decline in soil moisture across the globe, even in areas that may receive similar or even slightly more precipitation. These models also predict that Arctic sea ice, which is a resource that many Arctic animals rely on for nesting and hunting, will continue to decline in the years to come, and possibly it won't exist at all shortly after the year 2050. So if we continue to increase emissions as the more dire models predict, then there will be essentially no sea ice left in the Arctic after about 2050. However, if we are able to decrease emissions to zero carbon emissions by the year 2050, as the more optimistic models show, then we will be able to preserve some of that Arctic sea ice. So just as a reminder, Arctic sea ice melting does not contribute to sea level rise because that water that's in the Arctic sea ice is already in the ocean. So it's not adding to sea level rise if it melts. But melting of ice sheets in areas like Antarctica and Greenland, coupled with melting of glaciers in places like Canada and Alaska, this will lead to an increase in sea level rise or increase in sea level over the next 100 years and beyond. So the different models predict a sea level rise of about 0.5 meter or 1.5 feet under the best scenario, and up to 1 meter or 3 feet under the worst scenarios. These models all assume that the ice sheets are relatively stable, but if that is not the case. So there is a lot of research being done on some of the ice sheets, especially in Antarctica, because we aren't 100% sure how stable they are. If they are not stable, it's possible that sea level could rise 1 to 2 meters, which is about 3 to 6 feet. And then if you look out to the year 2300 and look at all the warming and impacts long term into the year 2300 relative to 1900, even the most optimistic models predict a sea level rise of 1 to 3 meters by 2300, with the possibility of a 15-meter sea level rise, which is about 45 feet by the year 2300. And this would flood many, many of the major coastal cities around the world. So just to summarize, these models are predicting increases in global surface temperature, in the amount of extreme heat events that we experience, flooding in some regions, droughts in some regions, a sea level rise, an increase in soil moisture evaporation, which will lead to drought, and then a loss of sea ice, an increase in the loss of sea ice, which means a decrease in overall sea ice over time.